Good day from Chem Help ASAP. Let's look at one last output file to finish our playlist on MO theory. In the upper left is formaldehyde, and the MO output file fills the screen. The carbon, oxygen, and 2 hydrogens in formaldehyde have a total of 10 valence atomic orbitals. So the molecule has 10 molecular orbitals. They correspond to the 10 columns in the output file. Formaldehyde has 12 valence electrons. Those 12 electrons fill 6 MOs. So MO number 6 is the HOMO, highest occupied molecular orbital. And MO7 is the LUMO, the lowest unoccupied molecular orbital. Let's think about the reactivity of formaldehyde. As a carbonyl compound, it is an electrophile. Electrophiles tend to react through the LUMO. The LUMO is a vacant orbital and can accept electron density from a nucleophile. Notice that the LUMO, MO7, has coefficients from the py orbitals of carbon and oxygen. This LUMO is a pi bond. Furthermore, the coefficients have the opposite mathematical sign. One is plus and one is minus. This pi bond is actually the pi star, not the bonding orbital. If you look at the coefficients, the oxygen py has a value of 0.59. The carbon py is minus 0.81. Ignoring the sign, we can see that the magnitude of the carbon py is larger. That means that if a nucleophile attacks formaldehyde, it will attack at the carbon preferentially. Attack occurs at the larger coefficient. Of course, we can draw this out at the bottom of the screen. Formaldehyde gets attacked by a nucleophile at the carbon. It breaks the CO pi bond and forms a tetrahedral intermediate. But we already knew this without MO theory. When you first learned about nucleophiles attacking carbonyls, you likely envisioned the CO pi bond being polarized. The resulting partial plus on the carbon attracts the nucleophile, and you form a tetrahedral intermediate. So why would you need MO theory when we could figure this nucleophilic addition without all these output files and orbital coefficients? Well, you're right. We can figure out carbonyl additions without MO theory. There are, however, many more subtle reactivity questions in chemistry, questions that are not obvious. Molecular modeling with MO theory can help us make more accurate predictions for these more difficult cases. In this playlist, we have only scratched the surface of what is possible with reactivity predictions through MO theory.